Okay, let's jump right in. If you're in college, maybe you're looking at a calculus problem set right now thinking, uh, seriously, when am I ever going to use this?
That's a very familiar thought for a lot of students, definitely.
Right, but what if those exact math tools you're grappling with,
Hmm.
what if they're actually used to predict something really every day? Like how long the food in your fridge is actually good for?
It's completely true. So today we're doing a deep dive into some interesting source material. It's an article looking at math and food security called Predicting Shelf Life Using Decay Rates.
Mm-hmm.
And right at the core of it are those calculus concepts,
Mm-hmm.
differentiation and integration.
Exactly. The source basically points straight at how these tools are, well, essential for understanding how food degrades over time
Yeah.
and predicting it.
And what's really key here, according to the source, is understanding that food spoilage, bacteria growing, enzymes breaking things down, chemical changes, it's fundamentally a process. It happens over time.
It's not static, it's dynamic change. So how does the math actually capture that kind of dynamic change?
Well, okay, differentiation. That's the tool for figuring out rates of change, like at any specific moment.
Correct.
Our source explains you can use it to model the speed at which spoilage is happening right now. Think about how fast bacteria might be multiplying, or how quickly some chemical reaction is going at a certain temperature at a certain time.
Ah, okay. So it's like measuring the speed of decay, but at this exact second.
Exactly that.
Oh.
And that speed, that rate, it often isn't constant. Spoilage might speed up, it might slow down.
Right, depending on things like temperature or whatever.
Conditions matter.
Got it. So differentiation gives you the speed of decay,
Yeah.
but shelf life, that's about the total amount of spoilage over a period, isn't it? How much is degraded overall?
Yes, and that's where integration comes into the picture, just as the source lays out. If differentiation gives you the rate, the speed at any instant,
Yeah.
integration lets you sort of sum up or accumulate that rate over a stretch of time.
Accumulate, okay.
By integrating that decay rate function, you can calculate the total accumulated degradation, the total spoilage that's happened over hours or days or weeks.
Okay, I think.
Yeah.
Yeah, I'm starting to connect the dots here. So the source is basically saying, use differentiation to find the formula for how fast it's decaying at any time.
Correct.
And then use integration on that formula to find out the total amount of spoilage up to a certain point in time.
That's the fundamental idea the source presents. It gives you the mathematical framework. You model the rate with differentiation based on data you observe.
Right.
And then you integrate that model to predict the extent, the amount of spoilage over some future time. So for instance, if the source shows a decay process following, say, an exponential rate, differentiation helps you analyze that rate's behavior, and integration then calculates the total effect of that exponential process over the product's life.
Wow, okay. That's actually pretty powerful. So you can literally project forward, predict when the total spoilage hits some critical level, like when it's not safe anymore or doesn't meet quality standards. This isn't just theory then. This is actually how they figure out those best buy dates you see on packaging.
That's exactly the application highlighted.
Right.
The source emphasizes that predicting shelf life isn't just, simple guesswork or drawing a straight line on a graph. Real-world decay is complex.
Right.
Using differentiation and integration allows scientists, food engineers, to build much more accurate dynamic models of these spoilage processes. It's taking that calculus from the classroom and applying it directly to a very real, very practical problem in the food industry.
So the mission for this deep dive was really to nail down this relationship from the source. How differentiation and integration are shown as these core mathematical levers for understanding decay rates, these dynamic rates, and crucially projecting them forward to predict shelf life. It really shifts calculus from just abstract ideas to, well, a tool used every day for food safety and even reducing waste.
And if you step back and look at the bigger picture, it really underlines that math isn't just developed in isolation, right? Understanding how things change, how they accumulate over time. That's vital in so many fields.
Absolutely.
In food science and engineering, like we've seen, it's about predicting spoilage for safety, for logistics, for purely economic reasons too.
So tying this back to you, the listener, what this all means is that those equations, those concepts you might be studying in calculus, they aren't just drills. They are literally the language used to describe and predict change in the real world.
Exactly. Shelf life is just one clear example where understanding rates and accumulation is absolutely key.
The so what here really is that Getting a handle on these mathematical tools gives you a powerful lens, a way to analyze dynamic systems
Mm.
and solve very practical problems, not just in textbooks, but out there in actual industry.
It equips you.
So maybe think about that next time you check an expiration date. It's a prediction, and it's rooted in the very math concepts you might be learning right now. And then, maybe let your mind wander a bit. Think about all the other places in the world outside the classroom where you see decay or growth or change over time.
So many examples.
Yeah. Could be how a medicine breaks down in your body, how pollution spreads, maybe how materials just age over time. And think about how math, like differentiation and integration, might just be the absolute key to understanding it, modeling it, and maybe even predicting what happens next.